Section 1.5 in our book is an introduction to limits. Now, in a sense, we've already been talking about limits, but we haven't used the language. So this section introduces the language and gives some examples. I want to point out that this isn't the precise definition of limits don't occur in this section. That happens a little bit later because it's kind of a complicated definition. So we want to get a sense, sort of a general feeling of what limits are and a lot of examples before we try to look at a specific definition, because it is a hard definition to understand. That will happen later. Now, limits are the basis for all of calculus, so you have to understand this. Everything this semester, everything next semester, everything you ever do with calculus will in some way depend on understanding limits. When I say we've already talked about limits, what I mean is we've talked about this velocity thing. We can measure velocity between 2 points in time, but if we are interested at one specific moment in time, we can't quite do it. The definition of velocity breaks down. So we have to do this thing where we use information really near this point to get an idea of an instantaneous velocity. Right? So instead of looking at one particular point, which is what we'd really like to do, we have to kind of look near it. And that's the idea behind limits. So the goal for this section is to find a systematic way to talk about what happens to a function, what happens to its output values, when the inputs are really, really close to one particular value. Right? And we'll make precise really, really close in a later section. For now, we're just going to say really close. Okay, so for example, here's a function, f of x equals x squared over x, and I know you really, really, really want to cancel an x and write f of x equals x. But it's not the same function, right? This function that I've written down, if you plug in x equals 0, you get 0 over 0, and that's bad. If I just wrote f of x equals x and I plug in x equals 0, it'd be fine. So this is a slightly different function, and this is the one I want to look at. So I'm going to make a table of values, right? If I plug in x equals 1, 1 squared over 1 is 1. If I plug in x equals 0.5, half squared over a half is a half. 0.1 squared over 0.1 is 0.1. 0.002 squared over 0.002 is 0.002. But 0 squared over 0 is undefined, so x equals 0 doesn't work. Okay. Now there's no reason I'm only using positive values. I could use negative values. I could plug in -1 or -0.5 or -1,000,000 or any number except 0 would work in this function, and if I had a little more space I would have made a table that included some negative values. Right. If I make a table with a lot of values, I can graph the function, or you could probably graph the function using other methods, but one way to do it is with a table of values, and what you'd see is this looks just like the line y equals x, except right at x equals 0, there's a problem. So right at x equals 0, the function doesn't exist just for a split second, and so we put an open circle there to indicate there's a hole in the line. There's a hole, a tiny, tiny gap in that line at x equals 0, y equals 0. But other than that, it's the normal y equals x diagonal line graph. Okay, so when I look at this, or when I look at the table of values, what do I see? I see, well, there's this weird thing that happens at x equals 0, but I can kind of tell what the function wants to do. As you head towards x equals 0, the function is headed towards y equals 0. It just doesn't ever quite get there, right? So when the x values head towards 0, the f of x values, the y values, also head towards 0. That's what happens to this function near x equals 0. A shorter way to write this, using some symbols, is as x approaches 0, and we write a little arrow for approaches, f of x, the y values, also approach 0. So as x approaches 0, f of x also approaches 0. And this is the language we'll be using, and we'll also sometimes write it a different way with an equation. Okay, so we have this language as x approaches a particular value, which now I'm going to use the variable a. F of x, the outputs, approach another particular value. In this case, I'll use the variable L. So as x approaches a, f of x approaches L. It's a perfectly nice sentence. It's a good thing to say. It rolls off the tongue nicely. But sometimes we would like a mathematical sentence that is an equation rather than an English sentence with punctuation and so on. So first I'm going to write it in a more complicated English sentence and then in an equation. So here's another way to say this. Oh, before I do that, let me point out that as x approaches a does not mean x equals a. It means x is really, really close to, but not exactly equal to a. And f of x approaches L means f is getting really, really close to, f of x values, the y values are getting really, really close to y equals L, they may or may not actually get there. Okay, so here's the more complicated sentence, and it uses this word limit. The limit of f of x as x approaches a is L, right? So this is the same sentence. It means exactly the same thing as what's written above. As x approaches a, f of x approaches L. F of x has a limit of L. And we can write this with the LIM stands for limit, x arrow a stands for x approaches a. I'm talking about the function f of x. And this is L, it equals L. So here's the equation. The limit as x approaches a of f of x equals L. This is a thing that is really important to understand. When you see something like this, if it doesn't already make you think of a full understanding of what's going on, it should in a few days. Right? So the picture in your head, if you think in pictures, should look like this. X is approaching a, so a is on the x-axis. F of x is doing something about L, so that's a y value, it's on the y-axis, and something's happening when x is near a and y is near L. So this spot where x equals a, y equals L, something's going to happen there. There's a highlighter here in the picture. And what's happening is the function, the graph of the function, when the x values are close to a, the y values have to be close to L. Okay? So it can do all sorts of other stuff far away from x equals a, but when x is near a, the y values are sort of forced to be in that little tight bubble around L. Now, at x equals a, y equals L, there might be a hole, there might not, I don't care. There might be a dot somewhere else. But what happens when x is near, but not exactly equal to a, is that the y values for the function definitely stay very close to L. So this is the picture of a limit statement. You're looking at what happens along the graph of that function as you move towards x equals a, and you keep track of what the y values do. Okay, there's lots of variations on limits. You can sometimes only be interested in, or only be allowed to look at, what happens when the x values are getting close to a, but not from both sides, right? Not from bigger and smaller than a, but just from one side. If you write a little plus after the a, it means x approaches a from the right, and that means x values are a little bit bigger than a. They're a plus a little. If you write x approaches a minus sign, right, this is not negative a, this is a and then the minus sign, this is x approaches a from the left. That is, the x values are a little bit smaller than a. They're a minus a little bit. Right? On a number line, from the right and from the left makes sense. So you're looking at what happens only on the left side of a, but close to a, or only on the right side of a, but close to a. Another thing you can do sometimes is instead of x approaching a particular value, you'll want to be interested in what happens when x gets really, really big, or really, really negative big. And the shorthand for that is x approaches infinity, or x approaches negative infinity. Those aren't numbers, but they are shorthand ways of writing bigger and bigger and bigger and bigger. So what happens on a graph when x moves forever to the right or forever to the left? A simple example, what happens to the function 1 over x when x gets bigger and bigger and bigger and bigger and bigger? Well, we know the fraction 1 over something. The smaller, the bigger the denominator, the smaller the value of the fraction, right? 1/2 is much, much bigger than 1/1,000,000th. So as x gets bigger and bigger and bigger, 1 over x gets closer and closer and closer to 0, right? 0.00000000001, and so on. So as x approaches infinity, the function 1 over x approaches 0. It doesn't ever get there, because 1 over anything can't equal 0. But when x is really, really, really big, 1 over x is pretty darn close to 0. Okay, a couple of cautionary tales. Graphs and tables can lie. Some examples of this are in your book, examples 2 and 4, and to a lesser extent 5. Please read them. In fact, read the whole section, please. But if you must only look at a few examples, look at 2 and 4 and 5. Another cautionary point, this is often a confusing thing for students. X equals a, and what happens there does not affect this limit as x approaches a at all. not even a little bit. F of a, that is, what happens to the function when I plug in exactly a, is a totally independent thing from what happens when I plug in values near a, which is what the limit is about. Right, so for example, here's a function, and it's got this little hole in it. I'll call that x value 2 and the y value 6. So when I try to plug in 2 into this function, there's a gap. There's no y value associated. There's no piece of the graph there. There's a hole. So the function is undefined. F of 2 is undefined. But I can talk about what happens when I put in x values near 2. And when I put in x values near 2, I'm really close to that hole, and that's the y value equals 6. So this limit is 6. And the point is, that hole being there doesn't matter. Instead, I could fill in the hole, and the limit would still be 6. Or I could put a dot somewhere else at x equals 2. Here, I've got it at y equals 8 and x equals 2. And now, f of 2 is not undefined. F of 2 is 8, because the x value 2 corresponds to the y value 8. But that doesn't change anything about the limit as x approaches 2. That's still 6, because x values near 2 are nowhere near that red dot. They're on the rest of the graph, and they're still near y equals 6.